following podcast is taken from a webinar presented by Dr. Jose Santos from the University of Florida, titled Transitioning to Success, the Intersection Between Nutrition, Health, and Reproduction. To view the full webinar and access the slides referenced during this podcast, visit balchem.com/realscience and use the search bar to jump down to this webinar presented on November 2nd of 2022.
It's a pleasure to be here, and for the next 45 minutes, I hope I will spend a little bit of time with you exchanging some ideas related to the transition period and how that may impact the success of the subsequent lactation. And then I will touch on a few aspects on how nutrition may interact with that. So this is how I typically see the transition from the dry period to the point in which the cow leaves the fresh pen. So if we think about the activities that we typically perform on dairy farms, first thing, we plan a dry-off, which typically takes place based on when the cow became pregnant. So I'll make the case that cows should be dried off at about 230 days of gestation. And at this stage, we hope that cows have proper body condition. And what I mean by that is that they are neither over-conditioned or they are extremely emaciated. So in the 1 to 5 scale, we hope cows would be here with a body condition score between 275 and 3.25. And here we need to have a plan to control mastitis, to control lameness, to control infectious disease, and we typically would feed a diet to avoid over or under consumption of nutrients. Okay, so we don't want this cow to gain body fat, neither we want this cow to lose body weight. Okay, obviously she's going to be growing a calf, and there will be weight gain, but we don't want her to deposit excessive amounts of body tissue that is not just calf and uterine weight. And then this cow would be moved to a closeup group when she is about 250 to 255 days of gestation, approximately 3 to 3.5 weeks before the expect calving date, which for the Holstein breed today, gestation length is approximately 275, 276 days. Here, hopefully, we'll be able to properly group cows. And what I mean by that is to have multiparous separate from parous cows. And I'll make the 2 points that are important relative to that. We'll continue with our health program. And here, the main goal is to feed diets to minimize metabolic disorders in early lactation, because these problems here will set the cow back for a successful lactation, whether we think about survival, milk production, and reproduction. And then once this cow gets into the calving time, we hope that she will be in a comfortable place and will be assisted by trained personnel that knows when to intervene. At the same time, they minimize intervention and they also reduce calving-related disorders. So here's a trade-off between having reduced number of stillbirths at the same time that we don't cause excessive damage to the cow because of early assistance, particularly for newly parous cows that perhaps are delivering a male calf, that are the ones that are going to have a greater challenge at this point. Once this cow moves to the early postpartum period, we need a plan to monitor health for early diagnosis of disease, and we need treatments and therapy that are science-based at this point. So here we have to feed diets that do not limit voluntary dry matter intake. So we want to feed diets that we know that cow will be able to eat as much as she wants. And the goal here is to control excessive weight loss in cows, in particular excessive lipomobilization, which we can use as a thermometer, subclinical ketosis. So we can use this just to guide us whether these cows are losing excessive amounts of weight or not. And the goal here is to minimize that. One aspect of controlling excessive body tissue loss is to have cows that have a proper body condition, and we have at the same time less disease. Then once this cow graduates from this fresh pen, which can last up to 4 weeks, in some farms maybe only 2 weeks, in some farms maybe a little longer, depending upon the calving flow of cows. Then she moves to a high group in which we're going to feed diets that maximize milk production and also facilitates the recovery of body condition. So those are sort of key goals of the transition period and key tasks that we typically implement in most farms. All of this we want to do with proper cow comfort and heat abatement.
New research is changing everything we thought we knew about choline's impact on the cow and her calf, and top scientists have a lot to say about it. They are presenting new research that supports choline as a required nutrient to optimize milk production, choline as a required nutrient to support a healthy transition, choline as a required nutrient to improve calf health and growth, and choline as a required nutrient to increase colostrum quantity. This new research is solidifying choline's role as a required nutrient for essentially every cow, regardless of health status, milk production level, or body condition score. Learn more about the science that is changing the game and the choline source that is making it happen. Reassure precision-release choline from Balchem. Visit balchem.com/scientistsay to learn more.
So let's look at the importance of cows spending time in this transition phase. So a few years ago, Achilles Vieira Neto, a PhD student now working with Merck Animal Health, he collected data from 2 herds over 3 calendar years, and we collect over 18,000 cow records from those farms that we monitor disease. And the disease we were interested were those listed here, calving problems such as dystocia and stillbirths, retained fetal membranes, metritis, respiratory disease, mastitis, displaced double mason, other digestive problems, and whether the cow died or not. And this all in the first 2 months of lactation. What we want to investigate and ask the question is, what is the association between time spent in the closeup group and the risk of this disease? For the sake of time, I'm going to show you the risk of morbidity, which is one or more of these events, what happens to milk production, and what happened to reproduction. So here is the risk of morbidity in the first 2 months of lactation for cows that are starting their second or greater lactation and cows starting their first lactation, the nulliparous cows. And we can see this days in postpartum group quadratic association with risk of morbidity. And what I mean by this is that the risk decreases as cows spend more time in the prepartum group, and then the risk increases as they spend excessive amount of time in the prepartum group. So there seems to be this sweet spot here, which is about 3 to 4 weeks, in which cows have the least risk of developing disease in early lactation. And if we have less disease, we expect to have greater milk production. So this is the cumulative milk yield in 305 days, divided by 305 days. Meaning that if a cow died early or if she was sold, she will contribute with milk for only the period that she survived. Okay, so this is accounting for deaths and culling. And you can see that cows that spend about 3 to 4 weeks in the transition group, in the prepartum group, had the maximum milk yield. And this should also reflect an improved reproduction, which is exactly what we see here. The proportion of cows that became pregnant by 300 days, and again, this accounts for cows that died, were sold, and never became pregnant because the producers decide to eliminate those cows. And we can see that the highest or the largest proportion of pregnancy happened when cows spend those 3 to 4 weeks in the prepartum period. So if we want to benefit from the things that we apply in the transition group, cows need to spend a minimum amount of time there. Now let's just look at this typical dairy cow on a farm. So this is your typical Holstein cow, okay, that averages peak milk yield at approximately 45 kilograms per day. So obviously many cows produce a lot more than that. But if you think of our average cow today, she requires this many megacalories of metabolizable energy for her maintenance. And then she needs this many megacalories of metabolizable energy for milk production. So to produce 45 kilograms of milk, which every cow will do at some point, or most of them will do at some point, she has to consume 70 megacalories of metabolizable energy per day. This means that if I divide this 70 by the maintenance, this cow is working at about 4.5 times her maintenance needs. Now, if we get extremes of the population, such as the current world record, this cow peaked at 123 kilograms of milk. And there are probably many cows that get close to this one, perhaps not 123, but many cows today produce 70, 80, 90 kilos at peak. So this cow is probably a little larger than this one. So she requires a little more, I'm assuming, for her maintenance. I don't have her body weight. But for synthesis of milk, she requires a lot more. So this is a cow that's working almost 9.5 times her maintenance needs. So it's obvious that cows like this, and as we have more and more of those, they are more sensitive to alterations and stress and stressors that can affect how nutrients become available to them, and that can affect long-term reproduction. So let's just look at this data here. These are data that we collect from a little over 5,000 cows, in which we took blood samples sequentially before the first insemination to determine whether these cows were cyclic or not. And then we asked the question, is there any association between the change in body condition in the first 65 days in milk and the probability of cyclicity, or the milk yield in the first 90 days in milk and the probability of cyclicity? So you can see clearly here that cows that lose excessive amounts of body condition, 1 unit or more in the 1 to 5 scale, a smaller proportion of them is cyclic by the end of the voluntary weaning period. So 58 versus 81%. So losing too much tissue is not good for resumption of cyclicity. Now, milk production, if anything, has a positive association with cyclicity. In other words, cows that are more productive, and this is the quartile within primiparous and multiparous that produce on average 50 kilograms per day in the first 3 months of lactation. And this is the quartile that produce only 32 kilograms per day. You can see that numerically the changes are small, but statistically it's a positive association. So we get more cyclic cows in those that produce more milk. Now let's look at pregnancy at first AI. We see the same association. A smaller proportion of pregnant cows when they lose too much body tissue. More pregnant cows when these cows suffer no change in body condition in early lactation. And if we look at milk yield, we see no relationship whatsoever. So my point here is that maintaining body tissue in early lactation or not mobilizing excessive amounts is very important. So how do we do this? We minimize the proportion of cows that are over-conditioned once they go dry, and we reduce the risk of disease in early lactation. So why am I telling you this? So let's just look at some mechanistic data here. This is a molecule of glucose, which is needed by many tissues, including the mammary gland, but also the central nervous system. And we know that the central nervous system, particularly the hypothalamus, is important to control reproductive cycles. This is another molecule that has a small alteration. You can see a replacement of this hydroxyl group by a hydrogen in this carbon here. And this small change here is enough to prevent the molecule to enter the glycolytic cycle. So it blocks glycolysis, meaning that it blocks the supply of energy for the cell. And the cells that surround the neurons, they require glucose. So what these people here did, they infused either saline in the fourth ventricle of the brain of ewes, or they infused this molecule to deoxyglucose that we know blocks the supply of ATP for the cells. And you can see that when saline was infused, these animals continue to have pulsatility of luteinizing hormone. And this hormone is very important to maintain follicle development, to induce ovulation. Whereas when they infused 2-deoxyglucose, they completely ablated the pulsatility of LH by the pituitary gland. So this is telling us that probably they block the release of gonadotropin-releasing hormone by blocking the supply of energy for those cells. So you can think that cows that lose too much weight or cows that don't eat very well in early lactation, they're going to have reduced concentrations of glucose because the mammary gland now is taking up most of it. And in those cases, reproduction will be set as a secondary plan. And obviously, extensive delay of cyclicity, which will happen in animals that have this, will set this cow back for reproduction. So let's think of this mechanistic approach. What we want is for cows at the end of the voluntary waiting period to behave like this one here, who is displaying signs of estrus. So this will happen if her brain receives sufficient signals, including what I call oxidizable metabolic fuel. So it can generate energy in addition to other endocrine signals. When this happens, we have signals for the pituitary gland to release hormones, such as follicle-stimulating hormone and luteinizing hormone. And this will maintain follicle development in the ovaries. Eventually, these follicles, or one of them, will produce sufficient estradiol that will signal the hypothalamus and the pituitary to have a surge of hormones that induces ovulation. And typically, ovulation follows this steroid-dependent reproductive behavior, such as estrus. However, when cows lose excessive amounts of weight, either because they don't eat very well, they have disease, or other factors, okay, this system is inhibited now. So now we don't have the normal pattern of LH release that supports follicle development. Therefore, this animal does not display signs of estrus. Consequently, she has delayed ovulation. She is the typical anovular cow. And those cows have reduced reproduction, as I just showed you. So we want to minimize the proportion of cows that suffer from this problem. Now, we know that energy balance or nutritional balance is an important drive for reproductive success. And if that's the case, we should focus on what affects nutritional balance. And what affects nutritional balance is dry matter intake. So here I have energy balance calculations for the first 60 days in milk out of 160 cows in which we had daily milk yield, daily dry matter intake, and daily milk composition and body weight. And you can see that there is a linear and strong relationship between energy intake, in other words, dry matter intake, and energy balance. Whereas if we look at energy secreted in milk, in other words, milk yield and energy balance, the relationship is quite weak. It is negative, okay? As energy secreted in milk increases, energy balance becomes smaller, but that relationship is quite weak. So we should focus on stimulating cows to eat in early lactation. So my first take-home message is avoid excessive body condition loss with the onset of lactation. Cows should lose no more than 0.5 units. And for that, we should have cows and heifers that do not calve over condition. We want to have more cows calving like this, that we see a U and a V here between the ilium, the head of the femur, and the ischium. And we want to see almost none of the cows would have a flat back, or that have excessive fat in the ligaments, either in the tail or here in the ilium. So this poses a question, but what about feed efficiency now? Now we have markers to select cows for reduced feed intake for a given amount of milk production, which is what you have available as feed save, as a new trait that's available for the Holstein breed. So let me show you some data that we generated a few years ago in which we look at the most efficient cows and the least efficient cows in experiments that we conducted. These cows here produce exactly the same amount of energy-correct milk, but they ate 4 kilograms less. Okay, 4 kilograms less, 25 kilograms of dry matter per day versus 21 kilograms of dry matter per day in the first 15 weeks of lactation, with exactly the same amount of energy-corrected milk. So how can this be possible? Obviously, these cows here are different than these cows. We don't necessarily understand why they are that different or what makes that difference, but we know that they are different because they are able to produce the same amount of milk with a lot less feed. So people would probably ask, well, there might be negative consequences to that. So let's look at some data here. So we looked at the risk of developing disease in the first 90 days in milk. And I'm only going to show you the 25 percentile most efficient cows, those that eat less for the amount of milk produced, and the least efficient cows, the 25th percentile least efficient cows. There's about 100 cows in each of those two groups, in the two extremes of the population here. So you can see that the risk of retained placenta, metritis, mastitis, displaced double mason, so on and so forth, they do not change. In fact, the risk of morbidity in the first 90 days in milk is exactly the same, okay, about 40%. The proportion of cows that left the herd by 300 days in milk, either by culling or sale, being sold, it's exactly the same, about 10%. Well, you might ask, maybe reproduction will suffer. So let me show you another piece of data from the same data set. Now I have here about 850 cows that we have daily dry matter intake, and we calculate what's called residual feed intake. So these are the most efficient cows. These are the least efficient cows. You can see a difference of almost 4 kilograms of dry matter intake between them. These cows ate 1.9 kilograms less than expected. These cows ate 1.98 kilograms more than expected. They had exactly the same energy-corrected milk production in the first 15 weeks of lactation. So if you look at the proportion of cows that became do not inseminate, we see no difference here. And now let's look at some of the important traits for reproduction. All of these values are based on a diagnosis of pregnancy performed 74 days after AI. So this accounts for all the losses of pregnancy during early gestation. You can see that insemination rate did not change, about 67% between the two extremes. But pregnancy per AI was actually greater in the more efficient cows. And this results in a greater pregnancy rate, okay, in the more efficient cows. And with that, a larger proportion of those cows were pregnant by 300 days compared to the least efficient cows. And this is quite puzzling. How can these cows eat 4 kilograms of dry matter per day, less than these cows? They have exactly the same energy-correct milk, and if anything, their reproduction is the same or a little bit better. So I think at this point, we shouldn't be afraid of selecting for feed efficiency, although we should optimize intake in early lactation. Now, one thing that affects intake in early lactation is morbidity, because most disease in cattle or in dairy cows affect cows in the first 45 to 60 days of gestation. So let me show you some data here of disease that affect the reproductive tract. This is an histogram of when metritis is diagnosed. And this data was put together by a colleague, Dr. Clives Galvão, here at the University of Florida. You can see that we have the highest prevalence of metritis right here at the end of the first week postpartum. Now, if we look at this data from Eduardo Ribeiro from University of Guelph, you can see that of the disease that do not affect the uterus, still most of them affect cows in the first 3 weeks of lactation. So these are the first 3 weeks of lactation. And this histogram chart shows this skewed distribution because the risk of disease decreases as lactation progresses in most dairy farms. So if I overlay one figure with the other, what I come up with is that about a third of the cows are affected by disease in the first 3 weeks of lactation. And almost 80% of the first disease diagnosis occurs within the first 3 weeks postpartum. And obviously, the earlier disease happens, the longer the potential legacy effect of that disease event in the lactation. Having a disease event at 20 weeks postpartum, it's a lot less costly than having a disease event in the first 3 weeks of lactation, just because this here can affect the remainder of the lactation, so the next 35 to 45 weeks, whereas this here will affect only the next 15 to 25 weeks of lactation. Now, disease have a lot more to do with what happens to the cow than just that initial insult. So let's look at this experiment here that was conducted with beef cattle. This is a beautiful piece of data that I wish we had this in dairy cows. So what these investigators at Oklahoma State University did is that they catheterized animals in multiple blood vessels, in the portal vein, in the hepatic vein, in the mesenteric vein and artery. And by doing this and infusing a marker, they can calculate blood flow across of the portal drain viscera, across the liver, and across the total splanchnic tissue. But here's what they did. They had animals that were kept as control. So they received saline in the trachea. Or they challenged those animals with a bacteria, Mannheimia hemolytica, that induces an inflammatory response in the lungs. So they had animals that were fed and animals that were fasted. For this discussion here, I'm going to focus comparing the control with the animals that they induce an inflammatory response in the respiratory tract. And I want to make a parallel between this steer here and a cow that develops metritis, because they have many of the hallmarks of an acute inflammatory disease. Okay, so they have an acute phase protein response. The cow also does. They have destruction of tissue. You can see the cow also does, but they affect different tissues. So it may not be a perfect comparison, but it's probably the best that we have today. So this is the flux of amino acids. They calculate the flux of multiple nutrients, and I'm going to show you the flux of amino acids from his PhD dissertation. Every time the bar falls below the zero line, it means that the tissue is utilizing more than it produces. So there is a negative net flux. Every time the bar is above the zero line, means that the tissue, in this case, the liver, that's the tissue that we are looking at here, it means that the liver secreted more of that nutrient than actually extract. So nutrients are coming in from the hepatic artery and from the portal vein, and they are leaving the liver through the hepatic vein. So you can see that for essential amino acids, both are below the zero line. So the liver is extracting more than it can produce, because obviously the liver is unable to produce essential amino acids. Okay? But the interesting thing is that it's more negative for the animals that underwent the bacterial challenge. Now let's look at the non-essential amino acids, those that cells can synthesize. Now we see a positive flux for the control animals that receive saline, but continue to see a negative flux for the animals that had that bacterial challenge or induced inflammatory response. So if we look at the total amino acid flux across the liver, we see a big difference. So the difference here is about 2.6 moles per day in a steer that weighs about 400 kilograms. So if we do a quick calculation and we use the average molecular weight of the 20 proteins synthesizing amino acids, this 2.6 moles per day equates to about 380 grams of amino acid that is in the bloodstream. Okay, that's in the circulation. And if we use an efficiency of amino acid extraction by the mammary gland of about 0.69% of metabolizable protein into net protein in milk, that equates to the protein equivalent of 8 kilograms of milk or 18 pounds. So you can see that there is a shift in partition of nutrients with an inflammatory response that's pretty substantial if what happens in the steer equates to what happens in a cow with an acute inflammatory disease, for example, as postpartum metritis. So not only disease induces this sickness behavior that cows eat less, they don't feel like doing things, but alters also how the cow uses nutrients and places more nutrients now to fight the disease process, and less becomes available for production and growth. Now, this has to have consequences to reproduction, and we know very well. So let me show you some data in which we inseminated cows that we had previously diagnosed without any disease event in the first 60 days of lactation, or cows that had at least one disease event. And then we flushed those cows on day 5.5 to 6 after insemination, and we evaluate fertilization and embryo quality. So we recover 420 embryo oocytes, and we can see clearly here that fertilization was reduced. The proportion of live embryos was smaller, and the proportion of high-quality embryos was also smaller. If we remove the oocytes from the calculation, we see exactly the same picture. Of all fertilized eggs, the proportion of live embryos and high-quality embryos in these cows that were not superovulate. So this is what happens in a typical farm. So this was done in a commercial dairy farm. And you can see that we detect reduction in embryo quality, which means by day 1 or 2 after insemination, we have fewer pregnancies in those cows. Now, this must be a problem of high-producing cows. Okay, so we decide to go and investigate this on a farm with this type of cattle. These are Holstein Zebu crosses that produce about 7,000 kilograms of milk in a grazing type of system. So a cow that produces 15 to 16,000 kilograms of milk. And we diagnose disease. Ingrid diagnosed disease in those cows, and we segregate cows without any uterine disease and cows that had at least one uterine disease. And here includes metritis, clinical endometritis, and subclinical endometritis. So most of this uterine disease was composed by cows that had subclinical endometritis. In other words, we don't find clinical signs of disease in those cows, but they have an inflammatory response in the uterus. So what happened? The beauty of this study is that 100% of these cows only received timed embryo transfer. So they did not receive any AI. It's only timed embryo transfer. So we bypass fertilization in the very early stages of embryonic development. And these cows receive an embryo. So we looked, what was the service rate, or let's say, quote unquote, insemination rate, if you will. You can see that it's smaller for cows that had uterine disease, to a large extent because those cows had a smaller pregnancy per embryo transfer. By reducing pregnancy, you will also affect in service rate. And by doing this, we affect pregnancy rate. You can see that the 21-day cycle pregnancy rate was smaller for cows that were diagnosed with uterine disease in the first 32 days postpartum. Okay? And this results in an additional 32 days median days to pregnancy in cows that develop uterine disease compared to cows that did not have uterine disease. And remember, most of this uterine disease here is not necessarily a clinical disease that we see by just collecting uterine or vaginal discharge. So what's going on here? We think that this inflammatory response can alert the maternal immune, in addition to causing damage to the tissue, affecting fertilization, affecting the ovary, affecting the quality of the oocyte, and multiple aspects, but this also affects the ability of the uterus to sustain pregnancy. And for that to happen, the maternal immune system in the reproductive tract has to tolerate components of the embryo that have foreign proteins, such as the proteins that are induced by the fact that half of the genetic material of this embryo comes from the paternal side, what we call this paternal alloantigens. And we think that when we have an inflammatory response, in particular in the reproductive tract, this can affect the ability of the maternal immune system to tolerate those embryonic proteins, and that can induce increased pregnancy losses, among other factors. So, second take-home message, we need to stimulate intake. That influences nutrient balance, that affects resumption of cyclicity. Cyclic cows have increased estrus expression, pregnancy per insemination, and they are more likely to maintain their pregnancy. We also need to minimize disease because disease causes inflammation and tissue damage, and that alters how nutrients are used, and now it favors control of the infection and inflammatory response at the expense of growth and survival. And reproduction, I'm sorry. So the priority now shifts to survival, and this has long-term effects on reproduction. Now, let's just shift gears, and I'll give you a couple examples. If the goal is to reduce problems, we need to think about how we formulate diets that will improve reproduction, and we should focus on these two important concepts. We know that reproduction is reduced once we have disease. So it's obvious that we should formulate diets that reduce the risk of disease. That's the first aspect. And then we should incorporate nutrients that are known to show a benefit to reproduction in cows. So I'm going to give you a few examples just because we don't have time to cover, a very extensive area. So let me show you one nutrient that can influence the risk of disease or metabolic disorder. One of which is choline. Choline is this molecule that you saw in the video early on that once consumed can be utilized to synthesize this larger molecule here. Actually, there are many molecules that is called phosphatidylcholine that can be quite variable in its composition of fatty acids that's connected here to this glycerol molecule. And phosphatidylcholine is very important because it plays numerous roles, and it's part of every cell in the body. Okay, one of those roles of phosphatidylcholine is to be part of this large molecule that's called very low density lipoprotein. Okay, and phosphatidylcholine, which are the phospholipids in the surface of this large molecule, allows this lipoprotein to contain lipids in its core or fats in its core, and it contains proteins in the outside that allows it to be miscible in an aqueous solution. So in this experiment here by Dr. Marcus Zenobi, we induced cows to develop fatty liver, and then we fed increasing amounts of choline ion in a rumen-protected form. Okay? This is the concentration of triacylglycerol in the liver when cows were in the well-fed state. They were receiving the diet ad libitum. And then we restrict those cows for 9 days. And what happened was that hepatic triacylglycerol accumulate in the hepatic tissue. But the accumulation was less and less and less as the amount of choline ion consumed by those cows increased. So it shows here this linear decrease in triacylglycerol accumulation as cows were supplemented with choline ion. So choline, like for dairy cows, like in any other species, has this lipotropic effect, and we think is linked to the ability to synthesize and secrete lipoproteins to export lipids from the liver. Obviously, these cows have a smaller risk of developing fatty liver. And if that's true, this should benefit lactation performance. So here is a meta-analysis that Usman Arshad conducted to look at all the literature we could find with controlled experiments in which cows had a controlled diet without supplemental choline ion as a rumen-protected choline product, or they were fed some amount of choline ion in a rumen-protected form. So the names here on the left are the reference from the experiments in which choline was fed during the transition period. To be part of this meta-analysis, the treatment had to start prepartum and continue until at least the day of calving, but most of them fed cows until several weeks postpartum. So the way you look at this here, each row here represents a comparison between a certain amount of choline ion in a rumen-protected choline form compared with the control within that experiment. And you can see all the comparisons that are available here. The black dot represents the point estimate. The gray circle represents the weight of that comparison in the statistical analysis. And the horizontal line represents the 95% confidence interval. So here it gives you a very good idea how repeatable the results are. And in general, most point estimates fall to the right side of the central line. And the central line is basically where there is no difference between the treated and the control. And this here is expressed as what we call standardized mean difference, so number of standard deviations. And the response evaluated here is energy-corrected milk. So you can see that most responses fall to the right. Okay? And in fact, the overall response from this analysis show an increase in energy-correct milk of 0.38 standard deviations, which represents an increase of about 2.2 kilograms of energy-correct milk production per day in the first few months of lactation. So this shows that benefiting health has a positive impact on production. Now let me give you another example of a manipulation of the diet that provides benefits to health and production. So these are a list of mechanisms involved on how acidogenic diets prevent hypocalcemia in cows. Just quickly, when we induce a slight metabolic acidosis, we ionize calcium that's present associated with proteins or in the form of salts. So now we have more ionized calcium in blood. Acidosis stimulates the parathyroid gland to secrete more parathyroid hormone, which is one of the calciotropic hormones that control blood calcium. Acidosis increases tissue responsiveness to parathyroid hormone. And once PTH is more active, that induces more synthesis of active vitamin D3 in the kidney cells. So this hydroxylation of 25-hydrox-D3 into 125-dihydrox-D3 is stimulated. A very important mechanism of these acidogenic diets is to increase calcium excretion in the urine, because acidosis blocks a calcium channel here that is responsible for reabsorption of calcium that's present in the filtrate. So when the urinary pH is acidic, this calcium channel, shuts down, so calcium is not reabsorbed, and now the cow secretes calcium in the urine. And this increased secretion of calcium in the urine upregulates all the systems that control blood calcium before calving, one of which is increased calcium absorption in the gastrointestinal tract, which is illustrated here. And finally, this slight metabolic acidosis induces cells in the bone, these macrophages here, to scavenge the mineral matter of bone that releases calcium into the bloodstream. So these combined effects improve blood calcium concentrations and prevent cows from having clinical as well as subclinical hypocalcemia. So this should benefit animal health. And we know very well that risk of milk fever is greatly reduced by feeding acidogenic diets. But not only that, as you can see that the risk of retained placenta and the risk of metritis, two important diseases that affect the reproductive tract, they are both reduced as the dietary cation anion difference of the diet prepartum moves from positive to negative. So when we feed acidogenic diets, the risk of uterine disease decreases in dairy cows. And we know that uterine disease affect production and affect reproduction. And if we have less uterine disease, we should have improved production. And in fact, if we look at milk yield and fat-cracked milk yield, when we feed acidogenic diets, both of them increase in parous cows. Now, here's an important point. Remember that I told you that in the transition period, we hope to be able to group cows and heifers separately. One of the reasons is that heifers do not respond with an increased milk yield by feeding acidogenic diet. So we don't get that benefit from nulliparous cows. But we do get an important benefit of feeding acidogenic diets to parous cows because we prevent milk fever, we reduce the risk of uterine disease, and we produce more milk or fat-cracked milk postpartum. Now, an important aspect, and goes back to this grouping of cows, is that those diets should be fed only during the closeup period. Okay? So here's an experiment in which we fed exactly the same diet, but we manipulate the DCAD, and we offer cows the diets, the acidogenic diets, either for 21 days, the last 21 days of gestation, or the entire dry period, the last 42 days of gestation. And this is the rate of pregnancy in those cows. And you can see that the rate of pregnancy was faster for cows that received the diets for 21 compared to 42 days. And you can see that the cows that received the acidogenic diets for 3 weeks only produced more fat-cracked milk and more energy-cracked milk than the cows that were fed for 42 days. So we think that cows should not be fed acidogenic diets during the entire dry period. Forage quality is very important, and I think that's being neglected during this transition period. And this is a typical diet of a cow. It's composed of forage, a starch source, byproducts, protein supplement, mineral vitamins, and maybe a fat source. In this example here, I have a forage that is of moderate to low quality. So I have limited inclusion in the diet. Each square here represents a kilogram of diet. I have a total of 24 kilograms, or each rectangle, I'm sorry, represents a kilogram. Each square is half a kilogram. So I have 24 kilos, of which 10 kilos are represented by forage. If I feed more, these cows are not able to produce the 41 kilograms of milk with 3.7 fat, 3.2 protein. But if I have better quality forage, I can occupy more space on my diet with forage, which is typically cheaper and is typically healthier and safer for the cow. Okay, and that's what I'm doing here. Well, obviously, this is just a simulation. So let's see if this is real. So here's a beautiful experiment out of Cornell University by Bill Stone, in which they manipulate the type of corn silage that was fed during the transition period, from 3 weeks before to 3 weeks after calving. Only 6 weeks of intervention. And they follow those cows for 15 weeks after calving. So what were the treatments? It was a conventional corn silage or a brown midrib corn silage. So this has less lignin and the neutral detergent fiber is more digestible. So each kilogram of silage provides more nutrients for the cow. So what happened in the first 3 weeks of lactation? Cows that were fed the BMR corn ate 2 kilograms more. What happened after 3 weeks postpartum, once they all received the conventional corn silage? So no more treatment being applied here. They ate the same. Okay? But now look at the fat cracked milk. It was always greater for the cows that receive the more digestible fiber source coming from corn silage. They produce here 4 kilograms more milk in the first 3 weeks, and they continue to produce 2.7 kilograms more fat cracked milk after these cows receive exactly the same diet. Okay, so that's another example of a dietary change that benefits transition cows. Now, my last point is something that can benefit reproduction directly. So this is an experiment from Jonas de Souza and the group of Adam Locke at Michigan State, in which they supplement cows they fed cows a diet without supplemental fat control, or they add 1.5% additional fatty acids with different combinations of fatty acids. So I don't want to touch on the different combination of fatty acids. I only want to look at the effect of fat feeding, which is the average of these three groups, versus control. And you can see that there was no difference in dry matter intake in the first 3 weeks of lactation. So supplying 1.5% of the diet dry matter as supplemental fatty acids did not depress intake in early lactation, but it did stimulate energy-corrected milk at those cows. They produced 5 kilograms more energy-corrected milk in early lactation. So you can stimulate production. Now, what happens to reproduction? So here's a meta-analysis from the Australian group, Dr. Ian Lean and his students, in which they pull data from the literature and they look at 17 experiments with individually fed cows that included 26 comparisons between control or some amount of supplemental fatty acids added to the diet starting in the transition period. They had almost 1,400 cows. There were multiple fat sources used. But here's the overall message from that meta-analysis. There was a 27% increase in risk of pregnancy, meaning that the controls would average 32, the treated would average 40%. So a substantial increase. And this resulted in a tendency for fewer days open. These cows tended to produce more milk. The milk composition didn't change, and these cows did not change. There was no change in body weight, no difference in body weight changes between the control and the treated animals. So improvements in reproduction without negative effects on body tissue and with additional milk production. So diets of early lactation cows should contain some amount of supplemental fat, and we should limit the total fatty acid content to somewhere between 4 and 5% of the diet dry matter. So just to finalize, here are some important points. Feed prepartum diets to supply sufficient energy, and you can look at what these values should be. The new NASEN 2021 provides good information on that. Supplement rumen-protected choline if the goal is to reduce the risk of hepatic liptosis and improve milk production in early lactation. Formulate diets with a negative DCAD to prevent hypocalcemia and the negative consequences of low blood calcium, such as uterine disease, metritis, retained placenta. Move these cows to the closeup when they are about 3 weeks before the expected calving date. So move them when they are between 250 to 255 days of gestation. Segregate nulliparous from parous cows. One reason is protein needs, the other one is the response to acidogenic diets, and the other one is just cow behavior. I'm not going to touch on this here. Postpartum, feed high quality forages. This is usually better, healthier, and often cheaper. We didn't talk about this, but protein in the early lactation diet is quite important. Be careful to not have limited protein diets in the first few weeks of lactation, because this can compromise productive performance. And supplement moderate amounts of fatty acids to improve fertility. Anywhere between 1 to 1.5% of the dry matter as supplemental fatty acids should be added to the diet.
Tonight's last call question is brought to you by Niasure Precision Release Niacin. Niacin is a proven vasodilator for heat stress reduction and a powerful antilipolytic agent for lowering high blood NEFA in transition cows. Protected with Balchem's proprietary encapsulation technology, you can be sure it is being delivered where and when your cows need it. Learn more at balchem.com/Niasure.
Jose, your first question is related to the dry cow period. It says that it seems that the single dry cow group management has become more popular recently. Many dairies do this to improve labor efficiency. What does a cow miss out on when managed in a single dry cow group? I think that's also relevant, right, to our some of our European producers as well that have only one cow dry group. Go ahead, Tom.
Yeah, so obviously when you do this is because you had either constraints in terms of facilities or you have this aspect of optimizing labor. It doesn't mean that it's better for the cow, so that should be clear, okay? So what we're missing is that obviously we're spending a little bit more money over the entire dry period doing things that probably the early dry cows don't need, such as some feed additives that are probably not needed in the diet. If we're feeding acidogenic diets, there's probably a negative consequence of feeding for the entire dry period, because acidosis has its role. It's beneficial for mineral metabolism, but it doesn't need to be fed for 45 to 60 days. And lastly, obviously, we would be spending money, for example, with additional protein in the diet, or if we are adding a little bit more energy in the close-up group, if we do this now for 7 to 8 weeks, there's a chance of cows accumulating a little bit more visceral fat, which is not advantageous to them. So if we have cows eating well, 12 to 13 to 14 kilograms of dry matter a day, becomes an issue formulating a single diet that prevents weight or body fat gain in the early dry period, and at the same time stimulates intake once they get closer to calving. So those would be the major issues in my view.
All right, thank you, Jose. Gopal Swami is asking, what is the significance of lower urine pH values below 5.5?
Oh, that's actually not a good thing. So once you get cows to very low pH, which a lot of people do just because it becomes more consistent, but for the cow, that's detrimental. So if cows develop what we call uncompensated metabolic acidosis, they are unable to maintain blood pH. The first blood pH, so the first thing they do is they back off on intake. That's the first thing they will do. Acidosis suppresses appetite. But there are other consequences, one of which is that it inhibits insulin release by the pancreas and inhibit insulin action on peripheral tissues such as the adipose tissue. So when we induce severe acidosis in cows, let's say if your cows are having urinary pHs of 5.5, 5.2, not only they eat less, but now they also start to mobilize more adipose tissue. So this can set them up for other type of metabolic disease such as fatty liver, ketosis, and the reduction in dry matter intake may set them up for displacement of abomasum. That's not recommended. So if you're using acidogenic diets, target an average of 6.2, 6.3, and aim such that almost every cow is between 5, 8, and 7. So you have a variation among cows, but make sure that every cow is between 5, 8, and 7, with a mean for the group of about 6.2, 6.4.
All right. Jair is asking, do you see a potential for feeding specific fatty acids during the prepartum period?
That's an interesting question. I think there is, but we lack data, to be honest. So we know that fatty acids have this nutritional role, but they are also very active molecules. And it's probably possible to manipulate this inflammatory response that normally happens in early lactation by altering the types of fatty acids that we provide in the diet. So if you ask my feeling, but it's not backed up by really strong data, is that if we were to feed fatty acids of the omega-3 family, such as alpha-linolenic acid, eicosapentaenoic, or docosahexaenoic acids, and we were to enrich the phospholipid layers in tissues with those fatty acids, probably we could reduce an exacerbate inflammatory response in early lactation, which would probably be beneficial to tissues such as the reproductive tract, or a general inflammatory response that would probably consume more nutrients than needed. So I think there is an opportunity there, but I don't think we know very well about it because we don't have enough experiments or data that have tested that hypothesis.
All right, makes sense. Muhammad would like to know your recommendation for using monopropylene glycol in the transition period.
Well, my recommendation is to not use unless the cow needs. And the cows that typically benefit from that are those, for example, that have excessive lipomobilization. So there's good data out of Wisconsin and Cornell showing that drenching cows with propylene glycol that have excessive ketogenesis has some benefits to reduce culling and subsequent disease such as displaced abomasum. But there's lots of data in the literature that giving propylene glycol to every cow, it shows improvements in reducing blood NEFA, reducing ketones, but usually you don't gain anything in production, health, or reproduction overall. So there are subgroups of cows that benefit from that, and maybe you might target those cows if you're screening, for example, for hyperketonemia. But given to every cow, I don't think that's recommended at this point.
All right. Dr. Chad Jenkins is asking, do you think there is a value to co-supplementing choline and methionine during the transition period, or does it make more sense economically to choose one or the other?
I think there is a role for both of them, my opinion. I think the importance of methionine in lactating diets is unquestionable. And I think the role of choline in the transition period is also unquestionable at this point. So if I could choose, or if I would feed choline, rumen-protected choline during the transition period, so starting at 250, 255 days of gestation and continue until the cow leaves the fresh pen. And I would definitely formulate for amino acids, which means include methionine in early lactation. There's probably a role for methionine prepartum as well, but I don't think we have those data just with methionine prepartum. So almost all experiments that have methionine transition period fed before and after. So we need some experiment that explore just feeding prepartum to understand whether that additional methionine, those extra 4 or 5 grams of metabolized methionine, plays a role in postpartum health and reproduction of cows. I think when you feed during the entire transition period, before and after calving, there's lots of very good data from multiple places that show benefits to that. What we don't know is just feeding prepartum is needed, because I can easily increase the overall metabolizable protein in the diet by just feeding a little more soybean meal or some other protein source.
Very well. We just passed the top of the hour. We have a lot more questions. Can you stay on for just a bit?
I'll be glad to.
All right. Very well. Yeah. Dr. Aldridge is asking, what is a mechanism whereby feeding low DCAD for 42 days versus 21 days had a negative effect on pregnancy rate?
Yeah, we don't know. I'm going to be 100% honest. Obviously, there are, that I'm aware, 3 experiments in which cows were fed acidogenic diets either for 6 to 8 weeks versus only 3 weeks. In all 3 experiments, energy-correct milk or fat-correct milk will reduce, at least numerically, not statistically, but the point estimate always went to the same direction. Okay? So when we pull those data from the 3 experiments, then I can show a statistical effect if I do a quick meta-analysis on that, analyzing those data. So your question is, why would reproduction be affected? So I can come up with some hypotheses. The first one is that acidosis, the only reason why at this point that we know of that we want to induce metabolic acidosis is to increase this flux of calcium through the body that prevents hypocalcemia. We don't have any good data to show that inducing metabolic acidosis per se without altering calcium or mineral metabolism is beneficial to the cow. In fact, if I do this during lactation, it's detrimental to cow performance. Cows eat a little less when they are fed during the entire dry period, so that may have some negative implications later on to health and reproduction of those animals. But we don't really know because we don't have extensive data on that. It's a single experiment with 114 cows, and that's what we observed. So there is some indication that's not beneficial, but we don't understand the mechanism. I think is related to the fact that metabolic acidosis was designed to prevent hypocalcemia, but it was not designed to have this overall health benefit to cows. And when we induce metabolic acidosis for too long, or if we have uncompensated metabolic acidosis, we can have those potential side effects, such as increased lipomobilization, reduced dry matter intake, that may have consequences to reproduction without understanding necessarily the exact cellular mechanism.
All right, thank you, Jose. Ahmed is asking, what could be the endocrinological interventions that we can do in transition period to stimulate dry matter intake?
Oh, that is the million-dollar question. Yeah, knowing what induces cows to eat more. I can come up with things that suppress intake, so you should probably avoid those. So heat stress, lack of cow comfort, disease, mud, excess undigestible fiber, excess rumen-degradable starch, excessive amounts of unsaturated fatty acids in the diet. All of those factors typically depress intake. So if I feed too much unsaturated fatty acid, I suppress dry matter intake. If I feed diets that are not digestible, particularly in early lactation, that will depress dry matter intake. If I have a system that has high prevalence of disease, it can be anything from mastitis, lameness, or anything, that will depress dry matter intake. That's a conserved mechanism. Cows that have pain or any disease or inflammatory response, they behave by eating. One of the behaviors is just reducing appetite. Okay? And that happens in cows, in flies, in whales, in any species that's being studied. So I think what we know is what to avoid. What we don't know is exactly what triggers the cow to eat more. Okay? So we need to do things that remove those obstacles and hope that this cow now can consume an extra 1 or 2 kilograms of dry matter. That's pretty critical, particularly in early lactation, to avoid displaced double Mason and other disease. Sorry that I don't have an exact answer, because I think we lack knowledge on that particular area. We know very well what's bad, but we don't know necessarily what triggers appetite.
All right. Cristiano is asking, I'm feeding anionic diets with particular DCAD in heifers as well, because it improves the uterine health after calving. What do you think about that?
Yeah, so we've done 2 experiments with just heifers here after that meta-analysis that we published a few years ago. So we had 2 experiments with about 230 heifers individually fed. And again, we replicated no benefit to milk production between an alkalogenic and an acidogenic diet. In one of the experiments, a moderate acidogenic diet, and what I mean by that, the DCAD was minus 50 milliequivalents per kilogram. For those that use 100 grams, is minus 5 milliequivalents per 100 grams. Those animals had a little bit better health. Morbidity was less in those heifers. In the second experiment, we fed minus 50 milliequivalents per kilogram versus, if I recall, plus 200. We had about almost 100 heifers, 50 per treatment. And we did not detect a benefit to health in those animals. So in the meta-analysis, if I go back and I showed you the data, you have to remember that 85 to 90% of the data came from experiments with parous cows starting their second or greater lactation. And mathematically, you don't necessarily separate the effect of the parous and nulliparous cows because you may not have enough power to detect an interaction for disease. Not every experiment reported disease incidence. So when we go from all the experiments that reported some of the aspects that we were interested on to uterine disease, we lose a lot of data because people just don't report when they publish some experiment, don't report some data when they publish experiments. So when we get down to the disease data, we may not have enough power to detect an interaction between DCAD and parity. So then if the interaction is not there, the point estimate is going to go in the same direction whether we have a heifer or a cow. And I'm not convinced at this point that we get the same benefits in health for the heifers. I think if we do, it has to be a moderate DCAD. You cannot go to the same level of acidoses as we typically use for cows. So we shouldn't be feeding a heifer a diet of minus 100 or minus 120 milliequivalents. That I feel very comfortable saying.
Well, this is a different question. I think it's a real one. I'm going to ask it. What about the use of endocannabinoids to increase feed intake?
Yeah, I will defer because I don't know enough data on that. And I think it's probably an area people are studying. There's a group in Israel and a group at Michigan State University studying endocannabinoids and their role in adipose tissue metabolism and appetite regulation. But I'm not sure if we understand exactly how it works very well in the cow, and how to implement that at this point. But I'll be glad to point out to people who probably will know better than I do in that area.
All right, thank you. Adrian is asking, regarding the data on disease and reproductive performance, what would be your comments on the 35% of no disease cows that did not get pregnant? What do you think are the main risk factors for poor fertility in non-disease cows?
There are many reasons, yeah. So you got to remember that disease is one component that can negatively influence reproduction, but I can come up with many reasons. So proper ovarian response to hormonal treatments. So let's say you have a perfectly healthy cow, but she doesn't completely regress the corpus luteum when you synchronize her for insemination. A little bit of progesterone can either block ovulation or block sperm transport. Your technician doesn't deposit semen properly. The semen quality is less than ideal. This cow is healthy, but she has hyperthermia. So there can be multiple reasons other than disease that can impair reproduction. And this is why you always have to think about populations, yeah? And you have to look at groups of cows and not just individually, particularly on herds. And unfortunately, there are many reasons, disease being one of them, that can affect reproductive performance.
All right, Jair is asking, what are the best hypotheses behind more efficient cows? What anatomical or metabolic effects could be implied?
Yeah, this is very puzzling, I have to say. And we have data in beef cattle. We have a little bit of data in dairy cattle. So I think they're obviously different. There are genetic differences and there are obviously major phenotypic differences. So I can come up with a few possible ideas, yeah? So those cows might spend less, may have less maintenance requirement. So we apply this rule of 100 kilocalories of net energy for every kilogram of metabolic weight as a rule for every cow, yeah? So if a cow weighs 600 kilos, and if I have 100 cows that weigh 600 kilos, they all have the same maintenance requirement. And we know that that's probably not true. So they may have differences in maintenance requirement. That's one of them. They may have differences in body composition that alters maintenance requirement. They may have difference in digestibility. So just how they digest feed. Maybe the more efficient cow she chews more. Her rumen microbiota is more efficient. Maybe the way the microbiota uses the carbon in the rumen is different, so favors one set of short-chain fatty acids versus another. Maybe they absorb better nutrients. Maybe during the post-absorptive metabolism, they have less futile cycles, so they utilize nutrients more efficiently. For example, let me give an example of amino acid utilization by the mammary gland. We know that different amino acids are extracted by the mammary epithelium with different efficiencies. We use a value, and I think the new nascent dairy cattle uses a 69% efficiency of amino acid extraction from blood into milk protein. So perhaps the more efficient cow has an efficiency of 75 or 80% amino acid efficiency. Maybe they degrade less protein in the rumen, so they preserve more amino acids. So proteolysis and deamination is altered, which favors amino acid absorption. So there are multiple reasons, yeah, and I don't have a good answer for your question, but I think we can address this in this segmental area until we come up with a good model for this more efficient cow. And I think this will be an area of research in the near future.
On behalf of Balchem and Dr. Santos, thank you for joining us today.
Hello, everybody. My name is José Santos. I'm a professor in the Department of Animal Sciences, and I want to take this opportunity to invite everybody to come to Gainesville next month to attend the Florida Ruminant Nutrition Symposium on February 24 to 26, 2025. So we've prepared an excellent program with the help of Balchem, Purdue Agribusiness, and other sponsors that will be probably very enlightening in terms of content, networking, and other opportunities. In this particular slide here, you have two links that can take you to our registration website, either to the symposium website or to the registration itself. As part of our program for the 2025 event, we have a mini symposium traditionally that's being sponsored by Balchem. So we are bringing Dr. Tara Felix from Penn State University, Dr. Brett Johnson from Texas Tech, Dr. Albert DeVries here from the University of Florida, and Dr. Tom Overton from Cornell University. And they are going to dive in and spend the entire afternoon discussing multiple aspects of beef on dairy, carcass composition, management aspects relative to the performance of those animals on feedlot, the economics of beef on dairy, as well as transition cow management, in particular the dairy cow, the transition dairy cow. So following the Balchem Mini Symposium, we have a traditional Brazilian, what we call churrasco or asado for those friends from the South, or a barbecue that you're going to be delighted to attend. And the following day, on Tuesday, we have a packet day with the morning being sponsored by Purdue Agribusiness, with a major focus on rumen metabolism and animal health. We have Dr. Jeff Firkins from The Ohio State University discussing aspects of rumen fermentation. Dr. Divakar Villas here from the University of Florida. Dr. Alex Bach from Spain, and Dr. Lance Baumgart from Iowa State University. So the whole morning will be taken by those 4 speakers with a lot of discussion, followed by a lunch, and then we have a full afternoon planned for that Tuesday, February 25th. So in the program of Tuesday afternoon, we have this lineup of speakers here on top. And for the Wednesday morning, we have this other lineup of speakers here on the bottom. So Dr. Bob Cousins, who is an expert on zinc metabolism and zinc transport, will start our afternoon program, followed by Dr. Dave Fraser from University of Sydney College of Veterinary Medicine in Australia. And we're going to finish our first session of the afternoon with Dr. Jerry Spears. So the whole goal of this first session in the afternoon is to really target and focus on mineral metabolism. Dr. Cousins will discuss zinc. Dr. Fraser will focus on calcium. And then Dr. Spears will talk about different sources of trace minerals for ruminants. So we'll have a break followed by 3 other speakers who will focus primarily on manipulations of the early calf and impacts on lifetime. So Dr. Jim Drakely from University of Illinois will talk about nutrient requirements of the pre-wean dairy heifer, followed by Dr. Javier Martin Terezo from Trouw Nutrition in the Netherlands. He's going to discuss experiments in which they manipulate the diet during the pre-weaning period and what impact that has on lifetime productivity. And then we have our own PhD student here, Mazur Sagir, who works under the mentorship of Dr. Pete Hansen, who's been doing experiments looking at manipulation of the medium in which embryos develop early on and what impact that has on the offspring. He's also conducted experiments in which he's strategically supplemented methyl donors such as rumen-protected choline, looking at potential impacts on offspring development in beef and dairy cattle. In the following day, we have a mixture of presentations focusing on newer methods to understand rumen fermentation using breath of cows, which is what Dr. Mutian New from Switzerland is going to discuss with us. So they have new technologies that can be used that are not invasive to evaluate ruminal fermentation. Then Dr. John Gieser will talk about new methods to evaluate forage quality and how that can play a role in diet formulation for dairy cattle. Our own Lais Lima, who is a PhD student under the mentorship of Dr. Divakar Vias, will talk about the experiments she's done looking at nutrient cycle on a farm, focusing primarily on nitrogen, but other nutrients. And then we have, again, Dr. Brad Johnson, Dr. Tara Felix, which will complete the program on that Wednesday, discussing impacts of beef on dairy on the cow itself, the cow that carries that calf. That will be some of what Dr. Tara Felix will discuss. So now going back of beef on dairy implications to the dairy cow, and Dr. Brad Johnson will discuss aspects of tissue deposition, adiposity, and muscle deposition in animals relative to interventions with beef on dairy. So we believe we have a attractive program with a lot of interesting information. Don't be shy to go to our website and check our program and opportunities to come and attend the conference. So I hope that you will come to Gainesville, particularly if you're from the northern states of the U.S. or Canada or other places. Come here to get a few days of collegiality. Defrost some, will be warm, hopefully, here in Gainesville, and enjoy this extension program. So I thank you, and I hope to see you all here in Gainesville next February.
We'd love to hear your comments or ideas for topics and guests, so please reach out via email at anh.marketing@balchem.com with any suggestions, and we'll work hard to add them to the schedule. Don't forget to leave a 5-star rating on your way out. You can request your Real Science Exchange t-shirt in just a few easy steps. Just like or subscribe to the Real Science Exchange and send us a screenshot along with your address and t-shirt size to anh.marketing@balchem.com. Balchem's Real Science Lecture Series of webinars takes place on the first Tuesday of every month, with the top research and nutrition topics that will impact your business. We also include small ruminant, monogastric, and companion animal-focused topics throughout the year. Visit balchem.com/realscience to see the upcoming topics and to register for future webinars. You can also access past webinars and search for the topics most important to you.